Good evening, ladies and gentlemen. This video is dedicated to my friends whom I met in the Department of Economics, University of Peshawar. And today I had an informal meeting with Dr. Amjad Amin Saab, Dr. Nadeem Saab, Dr. Mohammad Saeed, and some other. And on their request, I am going to upload a video which is based on binary logistic regression models. First of all, I would like to start with the introduction to binary logistic models. Basically, the ordinary linear regression has certain limitations, and one of its limitation is that the OLS regression cannot deal with the dependent variables that are dichotomous or categorical, meaning that if the dependent variable has two categories, yes or no, and they are coded like 0 and 1, then there is limitation of the conventional ordinary least square regression, and the result may not be then sensible. So there are many interesting variables in the world which are dichotomous, and the examples include, for example, consumers make a decision to buy or not to buy, a product may pass or fail quality control, there are good or poor credit risks, an employee may be promoted or not, and so on. A range of regression techniques have been developed by statisticians and econometricians for analyzing data with the categorical dependent variables, and those include linear probability models, probit models, discriminant analysis, and logistic regression. In this video, I will focus on logistic regression and binary logistic regression. Logistic regression is regularly used when there are only two categories of the dependent variable. Say, for example, the presence or the absence of certain characteristic, or say yes or no. Logistic regression is also easier to use with the SPSS software when there is a mixture of numerical and categorical independent variables, because it includes procedures for generating the necessary dummy variables automatically, requires fewer assumptions, and is more statistically robust. Thus, in instances where the independent variables are categorical, or a mix of continuous and categorical, and the dependent variable is categorical, logistic regression is a must. Logistic regression implies binomial probability theory in which there are only two values to predict. That probability P is 1 rather than 0, that is, the event or a person belongs to one group rather than the other. Logistic regression forms a best fitting equation or function using the maximum likelihood method, which maximizes the probability of classifying the observed data into the appropriate category given the regression coefficients. Since logistic regression calculates the probability of success or the probability of failure, the results of the analysis are in the form of an odd ratio, and an odd ratio is equal to the probability that the event will occur divided by the probability that it will not occur. So odd ratio is defined as P over 1 minus P. There are certain assumptions of logistic regression. Logistic regression does not assume a linear relationship between the dependent and the independent variable. Remember, in ordinary linear regression, the assumption is that there is a linear relationship between the dependent and independent variables. The second assumption of logistic regression is that the dependent variable must be a binary or a dichotomous having two categories. The independent variables need not be interval, nor normally distributed, nor linearly related, nor of equal variance within each group. And in case of ordinary least square, we assume that the independent variable may be of interval scale, and they may be normally distributed, and there is linear relationship, and the variance of the error term or the residual is homoscedastic, and so on. But in case of logistic regression, we don't need to assume all these assumptions. The categories or the groups must be mutually exclusive and exhaustive, and it means a case can only be in one group, and every case must be a member of one of the groups. Larger samples are needed in case of logistic regression than for linear regression, because the maximum likelihood coefficients are large sample estimates, and they say that a minimum of 50 cases per predictor is recommended. Let us suppose I start with a very simple case in which there is only one predictor, and that predictor is a dummy variable, and which has two categories. Now here you see that the probability of y, that is the probability of the outcome occurring, is given by 1 divided by 1 plus e raised to the power minus beta naught plus b1 x1 plus epsilon I, and rearranging this, we can write that probability of y is equal to e raised to the power beta naught plus beta 1 plus x1 plus epsilon whole divided by 1 plus e raised to the power b naught plus b1 x1 plus epsilon I, and the outcome is that we predict the probability of the outcome occurring. B naught and beta 1 are the coefficients. B naught is the coefficient of the constant, and B1 is the coefficient of the x1 variable, that is gender in this case. So beta naught and beta naught can be thought of in much the same way as in multiple regression, but we must note that the normal regression equation forms the part of the logistic regression equation. So these are two important things, that B naught and beta 1 can be thought of in much the same way as in case of multiple regression, and we may note the normal regression equation constitutes part of the logistic regression equation. Now we can extend the analysis with several predictors, and here we have x1, x2 up to xn variables, and in both the cases there are more than one predictors in this. So we still predict the probability of the outcome occurring. Note that the multiple regression equation forms the part of logistic regression equation again, and this part of the equation expands to accommodate additional predictors. Here we have more than one predictors. In the previous slide you saw that there is only one predictor. Now I will use a single dichotomous predictor, and that is gender of the subject. Let us first consider a simple bivariate logistic regression using subject's decision as the dichotomous criterion variable and their gender as a dichotomous predictor variable. It means the dependent variable has two categories, and the independent variable, that is the predictor, the gender, that has also two categories. In this analysis, gender is coded as 0 and 1, where one indicates that the gender is male and 0 indicates that the gender is a female. And decision is also coded as 0 and 1, where 1 indicates to buy a car and 0 indicates not to buy a car. And our regression model will be predicting the logit, that is the natural log of the odds of having made one or the other decision, and that is we can write this logit is equal to natural log of odds, and that is equal to natural log of estimated or predicted probability that the event will occur to the probability that it will not occur, and that is equal to B0 plus B1 x1. So the logistic regression equation basically estimates the logit or the log of odds, and that is equal to the natural log of the estimated probability that the person will buy a car to the probability that the person will not buy a car, and that can be written as a linear function of x1, where y hat is the predicted probability of the event, which is coded with 1, and that indicates to buy a car, rather than 0, which means not to buy a car. 1 minus I hat is the predicted probability of the other decision, and x is our predicted variable, that is gender, and it has two categories. 1 stands for male and 0 stands for female. So that is the basic idea, and this is a file in which here is the dependent variable, and that is a decision, and there are, sorry, let me go back. This is the dependent variable, and that has 0 and 1, where 1 means the decision to buy a car and 0 means not to buy a car. And there are many other variables, but I am just using this gender variable, where 0 stands for female and 1 stands for male. I will use this file later on, but let let me first open the file, and let me tell you the regression. Here I have just used these two variables, and I am going to run a binary logistic regression. My dependent variable is this decision, and my independent variable or the predictor is gender. Let me also show the variable view, and here are both the variables, that is the decision variable, and here are its codes. 0 stands for not to buy a car, and 1 indicates that a particular person takes a decision to buy a car. And similarly, there is a gender variable, and a gender variable is also a dummy variable, and here is its explanation. 0 stands for female and 1 stands for male. Let me go back to the data view, and let me tell you how to run a binary logistic regression. So I'll go to analyze, and then I will go to regression, and after that there are a number of options here, but I'm interested in binary logistics, so I will press this. When I press this, I will get this window. Let me take this out, and let me take this out so that you can see how we can run this regression. Here is my decision variable, that is my dependent variable, and this is my predictor, so I will send it here. If I press OK, it gives me output. So first of all, you see this shows data set 2, and this file is on my desktop, and this is the logit save. This is the name of the file, simple binary logit save. This is the SPSS file. Now this is the case processing summary, and it means that the total number of included cases is 315. So this sample size includes 315 individuals. There are no missing cases, so the missing cases are 0. So total cases included are 315. And here in this small table, as I told you, 0 stands for the decision not to buy a car, and 1 stands for the decision to buy a car. And then there is a block 0, beginning block, and SPSS basically starts with this block 0, beginning block. Let me do that with the help of explanation. So this is how we regress binary logistic model. If I scroll it down, here is the beginning. So case processing summary. Then there is the dependent variable coding. This is block 0 beginning block. Then there is a variable in the equation which is only constant. Then there is the chi-square score. Then there is the block 1 method, and in which the SPSS then adds the gender variable, and there is the chi-square statistic, and then there is the model summary, and it shows -2 log likelihood, Cox and Snell R square, and Nagelkarke R squared, and then there is classification table, and then there is the model variables in the equation, and it has the constant as well as the gender variable, and finally it is the case processing summary. So I have estimated this equation twice, so these are the same. Now let me go back to my presentation and I will explain these tables one by one. I was here in this model and I basically use these two variables, that is the gender, the decision and the gender, and I regress the decision on gender variable using binary logistic model. Now I'll explain the output. This is the first screenshot from the output, and as I told you, the SPSS has used 315 cases included in the analysis. There are no missing cases, so all of the cases are included in the model. This is the coding: 0 not to buy and 1 to buy a car, and this is the block 0 beginning block, and here is the explanation. And it says the block 0 output is for a model that includes only the intercept, which SPSS calls the constant. That is, initially the SPSS only takes into account the constant, and then later on it adds the predictor. Now, given the base rates of the two decisions, of the two decision option, one is 87, that is not to buy a car, and one is 28, and that is to buy a car, and the total number is 315. So 187 divided by 315 is equal to 59%. So it means that 59% decided not to buy a car, and 128 divided by 315 is equal to 41%, and it means they decided to buy a car and no other information. So the best strategy is to predict for every case that the subject will decide not to buy a car. Using that strategy, we would be correct 59% of the time. So this term 59.4% means that using this strategy we would be correct for 59% of the time. This is the second screenshot from the output, and here is the variable in the equation, and the SPSS has initially used only the constant, and the coefficient of the constant is minus 0.379. This is the standard error, this is the word statistic, this is the degree of freedoms, this is the significance, and that is the exponentiated B. If you raise the base of natural log to this value, then that will be equal to this value. So let me explain this. So under the variables in the equation, we see that the intercept only model is log odds is equal to minus 0.379, which is this. If we exponentiate both sides of this expression, we will find that our predicted odds, that is exponentiated beta, is equal to 0.684. That is, the predicted odds of deciding to buy a car is 0.684. Since 128 of our subjects decided to buy a car and 187 decided not to buy a car, our observed odds are 128 divided by 187, and that gives us this value 0.684, which is exactly this value. Now here is the variables in the equation, and here the SPSS has included gender variable in the model. So now the chi-square statistics is 25.685. I'll explain this a bit later. Now let me come to block 1, and block 1 is the model in which the SPSS has added the predictor with the constant. So this is the omnibus tests, and here is the explanation for this table, the omnibus test of model coefficient. Now if you look at block 1 output, here SPSS has added the gender variable as a predictor in this model. Omnibus test model coefficients gives us a chi-square of 25.653, means this, on 1 degree of freedom, which is significant beyond 0.001. This is a test of the null hypothesis. This is a test of the null hypothesis that adding the gender variable to the model has not significantly increased our ability to predict the decision made by our subjects. Since this chi-square value is significant, so it means that by adding gender variable to the model has increased our ability to predict the decision made by our subjects. Here is the model summary. There is a -2 log likelihood, and that is equal to 399.913. This is Cox and Snell R squared, and this is Nagelkarki R square. And now I will explain this. Here is the explanation of this model summary. Under model summary, we see that -2 log likelihood statistics is 399.913. This statistic measures how poorly the model predicts the decision. The smaller the statistic, the better the model. Although SPSS does not give us the statistics for the model that had only the intercept, we know it would be 425.66. Adding the gender variable reduced the -2 log likelihood statistic by 425.66 minus 399.913, and that is equal to 25.653, and this value is here. Okay, if we add this value to this value, then that would give us minus log likelihood for the model in which there was only the intercept, and that value will be equal to 425.666, and this 25.653 is basically chi-square statistic that we just discussed here in this block 1 output. The Cox and Snell R square can be interpreted like R squared in a multiple regression model, but Cox and Snell R square cannot reach a maximum value of 1, whereas in the classical multiple regression model, the maximum value of R squared could be 1 and the minimum value of R squared could be 0. But here in the binary logistic model, the value of Cox and Snell R square cannot reach the maximum value of 1. However, the Nagelkarki R squared can reach a maximum of 1. So keep that in mind. Here is the final model. We just discussed this. This is the classification table. Here are the predicted discussion, and here are the observed decision not to buy a car and buy a car, and these are the predicted not to buy and buy a car, and these are the various values. This 140 means that the predicted and the observed are correctly specified, and the observed decision to buy a car is not predicted by this model. So the overall prediction of this model is 66.0. Now here is the final model. Variables in the equation, the gender and the constant, and these are the coefficients. 1.217 is the coefficient of the gender variable, and minus 0.847 is the coefficient of the constant. These are the standard errors of the two coefficients, that is the standard error of the gender and that is the standard error of the constant. These are the word statistics, these are degrees of freedom, this shows p-value or significance value, and these are the exponentiated beta. And the variables in equation output shows that the regression equation can be written as log odds is equal to the constant, which is minus 0.847 plus the coefficient of the gender variable, which is 1.217, and here is the gender variable. Now let me explain this. We can now use this model to predict the odds that a subject of a given gender will decide to buy a car. The odds prediction equation is odds is equal to e raised to the power b naught plus b1 x. If our subject is a woman, that is the gender is equal to 0, then the odds are equal to e raised to the power minus 0.847 plus 1.217, and since the subject is a woman, so we will multiply the coefficient of the gender by 0, and that will be equal to e raised to the power minus 0.847, and its value is equal to 0.429, and that is exactly this value, for 0.429. What does it mean? It means that that is a woman is only 0.429 as likely to decide to buy the car as she is to decide not to buy it. This is technical. Consider it again. This odds equal to 0.429 means the woman is only 0.429 as likely to decide to buy a car as she is to decide not to buy it. If our subject is a man, that is when gender is equal to 1, then the odds is equal to a raised to the power minus 0.847 plus 1.217, and we will multiply that by 1 because this time the subject is a man. And if we simplify that, that will be equal to e raised to the power 0.37, and if you simplify that, then it will be equal to 1.448, and it means a man is 1.448 times more likely to decide to buy a car than to decide not to buy it. So this is how we explain this, and we can use these values, these odds, to probabilities. So it means this is the spelling is not correct. This is basically predicted or estimated probabilities, so I'm sorry for that. So we can easily convert odds to probabilities. For our women, y hat, that is the predicted probability that the event will occur, is equal to odds divided by 1 plus odd. So the odds for women was 0.429. So here the denominator will be 1.429 because it is equal to 1 plus odds, and if you simplify this, that is equal to 0.30. That is, our model predicts that 30% of women will decide to buy a car. What does it mean? It means that there is the probability of 0.30 or 30% that the women will decide to buy a car. For our men, y hat is equal to odds divided by 1 plus odds. Since the odds for the men are 1.448, so the numerator is 1.448, but the denominator is equal to 1.448 plus 1, so that will be 2.448, and if we simplify that, it will give us 0.429. 0.59. That is, our model predicts that 59% of men will decide to buy the car. The variables in the equation output also gives us the exponentiated B, that is better known as the odds ratio predicted by the model. You have already seen this in the output table, the variables in the equation. This odds ratio can be computed by raising the base of the natural logarithm to the bth power, where b is the slope from our logistic regression equation. For our model, e raised to the power 1.217, that was the slope. 1.217 was the slope of the gender variable. So we will raise that to the power e raised to the power 1.217, and that will be equal to 3.376, and that basically tells us that the model predicts that the odds of deciding to buy the car are 3.376 times higher for men than they are for women. For the men, the odds are 1.448, and for the women they are 0.429. So the odds ratio is 1.448 divided by 0.429, and that is equal to exactly 3.376. Now, in order to assess these models, the binary logistic model's output gives us a number of statistics, and one of them is the log likelihood statistic. The log likelihood statistic is exactly similar to the residual sum of square in the multiple regression. It means in case of OLS regression we use residual sum of square, but here we use log likelihood statistic, and the log likelihood statistic is an indicator of how much unexplained information there is after the model has been fitted. Large values indicate poorly fitting statistical model. So in a particular model that we have estimated, if the log likelihood statistic is higher, then it means that there is a poor fitting statistical model. If the log likelihood statistic is small, then it indicates that the fit is better. The binary logistic regression model also uses the chi-square, and it is possible to calculate log likelihood for different models and to compare these models by looking at difference between their log likelihood. That is, chi-square is equal to 2 into log likelihood of the new estimate minus log likelihood of the baseline, and there is some degrees of freedom from the new model minus the degrees minus the estimator in the baseline. Just like we use t statistic in OLS regression, here in the binary logistic regression we use Wald statistic, and in OLS model t is equal to the coefficient divided by standard error of the coefficient. Here in binary logistic model, Wald is equal to the coefficient, that is b, divided by standard error of b. So this is in a way similar to t statistic in regression, and it tests the null hypothesis that the coefficient is equal to 0. But keep in mind that it could be biased when b is large. So we must better look at the likelihood ratio statistic rather than the Wald statistics. Here is the assessing predictors, and these are the odds ratio, and the odds ratio are given by exponentiated beta, that is e raised the power the coefficient, and e raised the power the coefficient b is equal to odds after a unit change in the predictor divided by odds before a unit change in the predictor, and these indicates that is the exponentiated beta or the odds ratio indicates the change in the odds resulting from a unit change in the predictor. So the best strategy is to keep in mind, if odd ratio is greater than 1, then it means that as the value of predictor increases, the probability of the probability of outcome occurring is also going to increase. It means that when odd ratio is greater than 1, then it means that then there is a positive relationship between the predictor and the probability of the outcome occurring. In this case, of buying a car. On the other hand, if the odds ratio is less than 1, then there is an inverse relationship between the predictor and the probability of outcome occurring. And if the odd ratio is equal to 1, then it means that there is no relationship between the predictor and the probability of outcome occurring. This is a simple explanation of binary logistic model. Ladies and gentlemen, thank you very much for watching this video. I would like you to subscribe to the channel. The name of the channel is Research Made Easy with Himmy. Kindly share this with your students, with your colleagues, so that the benefit of this video can be increased, it could be maximized, so that more and more people can benefit from this video. But before I conclude this model, let me show. I just use in this example only one example because it's extremely technical to calculate these values, including log odds, the odd ratios, and the computation of the probabilities. But we can easily do that. Let me use this one, and here in this I will use a number of variables, not just one, and then you can see the output. So binary log, the decision is my dependent variable. I will click this variable here, I will click this variable here, and let me click this variable to be here, and so on. These are various variables, just and let me press OK. So I'm just giving you an example that where is my output? Sorry, let me check it again. This is let me go to analyze, and here is regression. This is binary logistic regression. Okay. Let me. Here is the new output. The total number of cases included are 315, and this is the dummy variable 0, 1. These are the predicted and the observed values, and these are the variables in the equation, exactly the same as before, and these are the case processing, and so on. So you can use as many independent variables that may be continuous or that may be categorical, but it's a kind of technical, and you can calculate the actual probabilities for given values of the independent variables, and you can also calculate the marginal probabilities in Excel very easily. Ladies and gentlemen, I hope you would have liked this video. If you like it, if you like it, you may submit your comments. If you have any question, you can ask me a question below this video in my YouTube channel. Thank you, and have a good evening.